In this video, we will define and calculate the heat exchanger unit operation as well as implement two logical operations, the balance and the adjust. We will also learn how to install a template file into an existing hysys simulation. In this video, a simplified refrigerated gas plant will be modeled to determine the operating conditions required to meet the product dew point target. In this scenario, the hydrocarbon dew point temperature of the product gas stream should be equal to minus 15 Celsius at 6000 kilopascal. This video includes the following tasks: build the base case, add a balance operation, configure and adjust operation, install a template. Task 1. Build the base case. The fluid package file, which was created in the Get Started video, will be used as the starting point for the simulation. By utilizing this fluid package file, you avoid the rework of the defining components and physical property options that are already available elsewhere. Let's get started. Create a new case. Select the fluid package folder. Click the import button. Select the gas plant fluid package file you exported during the Get Started video. Click Open. Review the data included in the gas plant file. You should note that both the Binger person property package and component list from the Getting Started video are in place. Click the Simulation Environment button to continue. Add a new material stream. Change the name. Set a temperature of 15 degrees centigrade. Set a pressure of 6200 kilopascal. Set a flow rate of 1440 kilogram mole per hour. Now let's define the composition of the stream using the following table. Now the stream is fully defined. Let's add a separator. Change its name. Set the inlet stream. Name the outlet vapor and liquid outlet stream. Now the separator is fully defined. Next, you will add a hysys heat exchanger unit operation. The heat exchanger performs energy and material balance calculation based on a shell and tube exchanger. Depending upon the input parameters, the heat exchanger is capable of solving for stream temperatures, pressures, mass flows, heat flows, including heat loss and heat leak, and UA. Double-click on the heat exchanger icon on the model palette. Change its name. Set the tube side inlet. Name the tube side outlet. Name the shell side inlet. Name the shell side outlet. Select parameters page and change the heat exchanger model to simple weighted. Enter pressure drop of 7 kPa for the shell side and 35 kPa for the tube side. And check Use FT checkbox. To solve the heat exchanger, unknown parameters such as stream flows and temperatures are manipulated by the solver in order to meet user-defined design specifications. Each design constraint that is entered will reduce the degrees of freedom for the heat exchanger by 1. In order to arrive at a unique solution, the number of constraints must equal the number of unknown variables. To solve for the unknown product temperatures in the gas-gas exchanger, 2 design constraints are needed. You will use the heat exchanger balance between hot and cold sides. This is a default and the minimum approach temperature specification. Select the specs page. Note the first listed specification mentions a heat balance. This specification is used to ensure that the heat transfer equations balance for both sides of the exchanger. As a default specification, it's always enabled by aspen hysys. Remove the default UA specification by deactivating the active checkbox. To add the minimum approach specification, click the Add button. Change the name to Temperature Approach. Change the type to Minimum Approach. Set Pass option to Overall. Set the spec value to 5 degrees centigrade. The minimum approach temperature defined is the minimum temperature difference between the hot and cold stream at any point inside the exchanger. The gas-gas exchanger is not yet ready to solve, as the shell side flow rate is not known. But make sure that your specification includes the minimum approach. The exchanger will solve once the remainder of the flow sheet is specified. Please note that you can have multiple estimate specifications. These are just used as initial conditions to help the exchanger solve. The heat exchanger will only use the active specification for the final solution. Return to the flow sheet and add a cooler operation. Change its name to chiller. Set the inlet stream. Set the outlet stream. Name the energy stream. On the parameters page, set delta P to 35 kPa. Add another separator. Change its name to LTS. Set the inlet stream. Set the outlet vapor stream and liquid outlet stream. The flow sheet still hasn't calculated from the gas-gas heat exchanger on downstream. The LTS separator is actually the critical item in this flow sheet. In fact, in order for the LTS separator to solve, temperature is required. In the next task, the LTS feed temperature will be varied using an adjust operation to find the temperature at which the dew point constraint is met. For now, you will simply estimate a constant value for this temperature. Set the temperature of the gas to LTS stream to minus 20 degrees centigrade. Now to our second task, add a balance operation. The balance operation provides a general purpose heat and material balance facility. There are several different balance calculation options available in Aspen hysys. The first balance type is component mole flow. That's an overall balance in which only the molar flow of each component is conserved. Combined outlet streams will have the same component flow rates as the combined inlet streams, but will contain no vapor fraction, temperature, or pressure values. The second type is mass flow. That's an overall balance in which only the mass flow is conserved. The outlet stream will contain no composition, vapor fraction, temperature, or pressure. The third type is heat flow. That's an overall balance in which only the heat flow is conserved. The fourth type is component mole and heat flow. That's an overall balance in which the heat and component molar flows are conserved. The last type is mass and heat flow. That's an overall balance in which the heat and component mass flows are conserved. If you open the property view of the cell's gas stream, you will notice that the three parameters are all calculated. So there is no direct way to calculate the dew point temperature at different pressure value. Adding a component mole flow balance allows you to create a second stream with the same flow rate and composition as the cell's gas without fixing the vapor fraction, temperature, or pressure. Add a balance operation. On the connection tab, set the inlet stream to cell's gas. Name the outlet stream. Under the parameter tab, set the balance type to component mole flow. Open the property view for the hydrocarbon dew point stream. Specify a pressure of 6000 kPa and a vapor fraction of 1. This will allow the hydrocarbon dew point stream to calculate its dew point temperature based on the composition. Now to our third task, configure and adjust operation. The adjust is another logical operation, meaning like the balance operation, it is a mathematical calculation rather than a physical unit operation. The purpose of AND-adjust is to vary the value of one process variable, the independent variable, to meet a target value or specification, the dependent variable. Add an adjust operation from the object palette. Click the Select Variable button in the Adjusted Variable group. On the object list, select Gas to LTS stream. On the variable list, select Temperature. Then click the Select Variable button in the Target Variable group. On the object list, choose Hydrocarbon Dew Point Stream. And on the variable list, select Temperature. Enter a value of minus 15 degrees centigrade in the specified target value box. Select the Parameters tab. Here you can specify a different tolerance or step size value from the defaults, or provide minimum and maximum allowable values for independent variable. In this case, the default settings are sufficient. Please note, when adjusting certain variables, it's often a good idea to provide a minimum or maximum which corresponds to a physical boundary, such as 0 for flow or pressure. Also, please take note of the step size used. When entering a step size, select a sufficiently large value, such that an approximate solution can be achieved in 2 or 3 iterations. Since the second convergence method works best once the solution has been bracketed, a larger step size ensures that you are more likely to bracket the solution quickly. It's also recommended to try a manual change of the adjusted variable prior to running the adjust, so as to vary the relationship between the adjusted and the target variables. Click Start to begin calculation. To show the progress of the adjust calculation, select and view the Monitor tab. To summarize, the temperature of gas to LTS has been adjusted to make the temperature of hydrocarbon dew point equals to minus 15 degrees centigrade. Now to our final task. Install a template. The current setup of your refrigerated gas plant uses a simple cooler model for the gas chiller. The next step will be to link the propane refrigeration loop we built in the last video to the chiller. Once linked, the refrigerated propane in the refrigeration loop will be providing the cooling duty to chill the gas. Select the standard subflow sheet from the model palette. In the subflow sheet option dialog box, select Read an existing template. Navigate to the template file you saved in the previous video. Select it and open. Please note that once a template is installed as a new subflow sheet, any subsequent changes only affect the template objects as they exist in the current simulation. These changes would not affect the template file from which the subflow sheet was derived. On the Connection tab of the subflow sheet operation property view, you can define all the inlet and outlet connection between the subflow sheet and the main flow sheet. Inlet connections are material or energy streams entering the subflow sheet. Output streams are streams leaving the subflow sheet. If the inlet connection to subflow sheet group box, click the external stream box next to chill queue and select a chiller queue from the drop-down menu. You will notice that the chill queue stream on the subflow sheet side is automatically renamed to match the main flow sheet stream name. Please note that the internal streams refers to the streams in the subflow sheet. External streams are located in the main or parent flow sheet. This concludes our video. In the next video, we will perform oil characterization and high pressure separation. Thank you for watching.